Hello everybody and welcome to the first tutorial on systems programming. Alright, first of all, let's start off with what you need to get started. So you'll need either a Linux or just actually any computer. So there are ways. So we're gonna today start off with assembly language. We're gonna dive straight into it, and from assembly language we might dive into some C. Alright, so for assembly language, if you have Linux, that's great. If you have Windows, that's also great, as you can get something called WSL, which lets you run Linux on Windows. If you have macOS, it's a bit of the worst side. There is a separate way of coding for assembly language in macOS, but I would say right now we're gonna stick to the Linux syntax way of things. So if you have macOS, you can either get a virtual machine, or you can use a website like this called an online NASM interpreter. So if you do online assembler, NASM compiler ID. This might be slightly different. Yep, so over here you can do all the stuff, run it all in, it gives you a result. It's not close to, I would say, as fun as doing it like on a Linux computer, and some quirks might be a bit different, but it stays relatively the same. Alright, let's get started. So first of all, I have myself a terminal right over here. You're gonna need a few dependencies installed. So you're gonna need this thing called NASM installed. If you're on Linux, you can simply use your package manager, so sudo apt install NASM, and you can get it. If you're on a Mac, you should probably use brew for macOS, which is Mac's version of a package manager. This again, if you're on a Mac and you're doing this, remember it's gonna be slightly different syntactically. We're gonna get to it later. What are some of the differences? But this is made for Linux, but you can follow along if you're on a Mac and running NASM on a Mac. It's just slightly different. Alright, so I'm on Linux right now, so this is how you install on a Mac. So right now you need NASM installed. You need something called LD installed, which should come with the base of your operating system, but if it doesn't, well, you need to have that installed. And you need obviously a text editor, so that's somewhere where you can edit your code. Alright, let's get started. So I'm in the terminal right now. Let me create a new file called main.assembly. So first, I'm gonna get right into it. So global underscore start section dot wait, you know what? Oh, let me actually just search up the hello world sort of assembly language, so I don't have to bore you with all the details. So hello world in NASM. Alright. Wait, let me actually just do x86. We'll get to what that is in a bit of time. Okay, let's see how this is. Alright, here it is. So, if I'm gonna just delete that, and let me copy that, and paste it into my editor. So I'm currently using Vim, or I'm actually technically using NeoVim, but they're quite similar. That's why some of the way I'm doing things might look a bit different, but not to worry. Okay, so now that I have the basic hello world, I'm gonna quickly just delete all of these stuff. And I personally like to use a different sort of format of like formatting things, where I'm gonna put the this data section at the start. Let me just do section.data. Alright, so what does this all mean? Well, this might be quite a lot to take in. Like, what is all of this move rex? Is this all, like, all of this is just for hello world? What on earth's going on? Let's start at the very beginning. So global underscore start. This basically just tells the program that you want to start where it says underscore start. So you want to actually start running the instructions at the underscore start label. Oh, also as a prerequisite for this, I assume you know most of the basics of the different components in the hardware, and like what a CPU means, what a CPU does. Alright, so global underscore start. This tells the computer you want to start at this function. It's sort of like how in C you do the you do int main, and then int main, and you have all your code over there. Same way with assembly, you do global underscore start to tell the program you want to start at the start label, and it starts right there. So you do underscore start and colon. So also in assembly, functions and like these are called labels are start with an underscore and are expressed that they start there with a colon and a new line. So that's just some syntactical things about assembly language, or the type of assembly language we're using. Alright, so move RAX1. What on earth does this mean? Alright, to begin with, we need to understand some concepts of the CPU. So the CPU has many different registers, so it's called. So let's say the registers A, B, C, D, E, F, G. Just for the examples of this tutorial. In these registers, you move values, and then the actual CPU just like manipulates its registers and then gives that register back. So for example, let's say you want to add two numbers, 10 plus 5, right? So you can move 10 to the A register. Let me zoom in actually. You move 10 to the A register, 5 to the B register. Then you tell the CPU to run the add instruction. So then it adds what's on the A and B registers to give you a new A register that's 15. Once you have that new A register, you can load it back into memory using something called like a load instruction. So there are lots of small instructions that overall end up making a program. So in this case, you first move the value of 10 into the register A, move the value of 5 into register B. Use the add instruction to tell the CPU that you want to add the values in the A and B registers, and then accordingly you can load it back into memory using the load instruction. Alright, so what is all of this? Okay, for now don't worry about this. So let's start with here. So section.data message db hello world. Okay, all this says is at the start. So section.data is just a syntactical thing, so you know that over here you're gonna put all of your data. I could very well just comment this line of code. Comments are done with semicolons, by the way. So I could very well comment the line of code, but I'm just gonna keep it there as it helps organize it. So message, it saves this part into memory. So it does message colon and then db, which shows that each of these represent bytes. So db hello world. So this is now hello world gets stored in ASCII, and rather than 0xa, and this is let me just do 10 so you guys can understand. And the comma 10 is the new line character. So 10 is the ASCII value for new line, and you can't use C style escape codes in NASM, so you have to say comma 10. So you also want to store the 10 value. So it stores hello world plus the new line at the end. So it stores this all in bytes in a memory address that we can later address by message. Now in the actual binary of this, there won't be any fancy sort of like message. It will just be referencing to a specific area in memory where it stored this in. But for us, we can just simply address it as message. So it sort of acts like a constant variable. And as this shows, it basically, in C, this is how it would be represented if you know anything about C. Let me just delete this rest of the comments. Okay. Now length. So this is another variable we're going to store, sort of like a constant, more of, that will be stored in memory, that will just say how long the hello world is, like how long is this string. This is so that the assembly will know how many characters to print out from this memory address. Otherwise, for example, if we say 1,000, let's say we don't like give it 1, or we say like infinity, it would keep, so go through the message address, since this is all stored in a memory address, then it would go through each byte, hello world, but it won't know where it ends. So we just keep reading hello world, and then it would go to the next address, next address, next address, even though it's not part of the message, which is why we have to give it a specified length. So in this case, we can count it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. We have to remember about the new line character at the end. So length as 13. Alright, now what on earth is all of this stuff, right? So you'll be wondering to yourself, let me also just quickly delete the spacing there. Alright, so what is all of this stuff? So section.text is, again, another syntactical thing, just to show, like, as the programmer, that the actual, like, text, the core of the program is starting now. I can't very much just delete that, nothing would change, but it's a nice thing to have. Alright, so move racks, comma 1. Now, as we just talked about, how you can move values into the registers, right? So all racks is it's basically that A register we were talking about. And then there's this, in the similar way, there's our BX, there's our CX, there's our DX, right? There are all of these different registers where you can move values into. Now, you might be asking, what's the R stand for? That just shows that it's a 64-bit address. Here, the R shows you're referring to it as a 64-bit CPU value. If I change this to something like EAX, that means I'm referring to it in 32-bit mode. So that's why, like, you might see programs differentiating whether you can get a program in 32-bit mode. So that means all of its instructions will be written in such a way that you can use something like EAX, which stands for 32 bits EAX. For this, we're going to be going with 64-bit mode, so that's RAX. So all 64-bit registers are represented with R, letter, and then something. So just, it starts with R. Okay, let me go back to where it was. Undo all of that. Okay, so move RAX, comma 1. So what we do is we load the value of RAX as 1. Now, over here, this entire chunk of code, basically, in assembly language, there's no just like straight up way for the CPU. There's no way, like there's no instruction per se for the CPU to print something in the console, since the console and like a terminal in general is handled by the operating system. This is why assembly language allows you to have things such as called system calls. It's called syscalls, or invoking the OS, like that. So it basically, you put a bunch of values into the registers, and then the operating system sees what those values mean. So, for example, having the RAX value as 1 shows the operating system that you want to write something out. Then having the value of RDI as 1 shows the operating system that you want to output something into console. And then you have to move the address of the message into the value RSI, and move the value of the length into the register RDX. So move the length value into RDX, and then you do the syscall. So you first move all the values into the registers, right? So you move all the values. Now, if the operating system can look at the different values of the registers and know what to do. So in this case, we wanted to print hello world to the console. So you can look at each of the values and see that, well, first of all, you want to write something out. You want to output it to a console. You want to write the message out called from the memory address message. From the memory address message, and you want to do the length as the number of the bytes, and that you want to actually print out. And then you could call the syscall to obviously just tell the operating system, okay, here I am, look at all the values and do it accordingly. So now this part prints hello world. Now this part, so you know how in all programming languages you can return the you can like exit and return the program with a different error code. It's usually represented as 0 being no error code, and any other value usually means some sort of different error code depending on the value. So like that's why in C, for example, at the end of your int main, you have like int main, you have return 0 to show that there was no error. However, if there was an error, you do something like return -1. In the same way, with assembly language, we have to tell it, okay, now we want the program to end, and we want to return a specific error code, right? So in our case, rather than doing this XOR, let me just do move, or wait one second, move RDI, comma 0. I don't know, that was an extremely like complex way of doing it for no reason, but this is it. So RAX as 60 is the system call for exit. So how, there was a system call for write, so that when you do syscall, it looks at the RAX value and sees like what it needs to do. So while 60 represents exit, and move RDI comma 0 means that you want to exit the program with an error code of 0. If I change this to -1, it's gonna exit the program with an error code of -1, and so on. I can change this to whatever I want. 20, it doesn't matter. I'm gonna stick with 0 for now. And syscall. Let me just delete that. And syscall to once again look at the RAX value, see it's 60, meaning want to exit, and exit with error code 0. Alright, so let's see what happens when I run this, shall we? Let me just delete these extra windows. So first of all, right now in this directory I have my main.asm file. Now first I have to compile it, so nasm-f elf64 main.asm. All this tells us is we're compiling this as a 64-bit binary file. Let me see what I messed up there. Give me a second. Start line 5. What is this? Parser instruction expected. I'm honestly not too sure why this is happening. Let me quickly check. Okay, cut forward. I figured out the error. So for now, let's just not have this length as 13 as a variable, because you need to mention the data type of it, which is keyword in this case. But for simplicity's sake, let's just not have this. And rather than moving RDX to length, let's just change it to moved straight to the value. So the value is 13. So you wanna, it shows that the length of this is 13. Alright, let me run this. So nasm-elf elf64. Now, as we can see, we've got a new file. So we have main.asm. Now it got compiled into a binary object. To make this an executable, we'll have to use a linker. So linker main.o ld main.o -o ./main. So, or just main. So this just parses like this binary file into an actual executable. So let me do that. ls. And now, as we can see, we have 3 files. Let me run it. So ./main. Hello world. That's our hello world in assembly language. Thanks for watching this first tutorial. Don't worry if you found it hard. It gets substantially easier as time goes on. Thank you.